Currently, BMP choices are based principally on minimizing the capital cost of installation of the BMPs. But as more and more cities are faced with meeting stormwater total maximum daily loads, or TMDLs, stormwater managers responsible for meeting those requirements are faced with determining which BMP LID practices or combination of practices will meet those TMDL requirements, and what will be the whole life cost of those alternatives. A recent product of the WERF Stormwater Challenge is a simple planning level tool called SELECT that enables a stormwater manager to examine the effectiveness of alternative scenarios for controlling stormwater pollution and the whole life cost associated with each scenario. The tool enables a manager to make informed decisions on which practices to permit with some confidence that they will meet the imposed TMDL limits and are affordable. SELECT is a simple BMP selection tool. It is encoded in an Excel 2003 spreadsheet, which means that it is intuitive and easy to use for most individuals. The control panel has several functional areas that guide users in setting defaults, inputting user information, and executing the model. The concept of SELECT demonstrated here is taken from the Corps of Engineers storm model. A long-term record of hourly rainfall drives the model. This hourly rainfall is translated into runoff using a runoff coefficient. The runoff is introduced to the BMP. If there's capacity in the BMP, the runoff is captured. If the BMP is full, the runoff is discharged untreated to the receiving waters. Input data for SELECT includes a long-term hourly rainfall record, which can be downloaded from the National Climatologic Center database, land use data, BMP information, and event mean concentrations for runoff and BMP effluents. Output data comprises annual pollutant loads discharged to the receiving water, pollutant load frequency curves with uncertainty estimates, and an estimate of the whole life cost of the BMPs applied in the watershed. BMP and water quality parameters that can be simulated in SELECT are shown in this slide. As time and funds permit, additional BMP and LID practices will be added to the model. If you would like to help expand the current set of BMP or water quality parameters in the model, please contact Jeff Moeller at WERF. His contact information will be provided at the end. The estimation of whole life costs is BMP specific and includes capital costs, O&M costs as a percent of the capital cost, and replacement or salvage cost at the end of the useful life of the BMP. The cost calculator is based on information and software developed in other studies. Cost data for extended detention ponds, retention ponds, wetlands, swales, and permeable pavement comes from a 2005 WERF study. The source for data for bioretention, green roofs, and cisterns is from a recent joint WERF EPA project conducted by the University of Utah, in which a spreadsheet tool was developed for estimating the whole life costs of 3 LID practices. The cost estimation tool for bioretention covers rain gardens, curb-contained applications, and in-curb planter vaults. The green roof costs tool evaluates costs for extensive green roofs. The tool offers 2 cost estimate methods. One is based on a pre-manufactured modular style installation, and the other allows for a custom installation. Cisterns are also covered in the LID cost tool as indicated on the slide, but they are not included in the SELECT model. This slide shows an example of the output from SELECT. It includes identification information such as the name of the modeler and identification of the watershed, echo print of the scenario input data, and results. Zooming in on the top portion of the report, we see the user information and the watershed scenario information. Note under scenario data that a watershed is comprised of subcatchments, but each subcatchment drains to a single BMP. The second group of scenario data identifies the BMPs that will be included in the analysis and the statistical properties of the effluent concentrations of those BMPs. These data can be obtained from data gathered locally or from the International BMP database. Note that water can be lost from the BMP by evaporation or infiltration. The third group of input data is land use-based event mean concentrations of the runoff. Again, Local data can be used or data are available in the international database. Now we scroll to the bottom of the watershed report. In the upper box we see a summary of the rainfall data that were used to drive the model, including the period of rainfall used, total rainfall that occurred during the period, and the average rainfall per event and the average annual rainfall. The results are summarized in the lower box. They include total and average annual values for runoff volume and pollutant wash-off from the watershed. For BMPs, the output shows the annual volume treated by the BMPs and the mass removed, the annual volume of runoff and mass that bypasses the BMPs untreated, and the total volume and mass discharged to the receiving waters. These data can be compared with TMDL limits to determine how close the scenario under investigation comes to meeting the criteria. An added feature of the model is computation of pollutant discharge exceedance frequency curves with confidence intervals. These are very handy for determining the frequency with which a designated load to the receiving water will be exceeded. Finally, we come to the whole life cost report. This report comprises 5 parts: user data contained in the watershed report, scenario data relevant to determining capital costs data specific to each BMP, O&M data specific to each BMP, a summary of the whole life costs of the BMPs for each watershed. That's how the model works.